variable, you can compute the gradient. So the gradient is at the point xy is 2x and minus 2y. And the action matrix is 2, 0, 0, minus 2. So you see that this matrix, it has one positive eigenvalue which is 2, and it has one negative eigenvalue which is minus 2. So it's a starting point. And if you apply Newton method to this case, then you can see that whatever x0, y0 you start with, you call the next point will be 0, 0, which is the starting point. Yeah, so it's not good because then you apply it to a general function and you choose the random point. Then that random point will be mostly close to a starting point, and then you apply this method, and it will convert to that starting point, and it's not converts to minima. It's not good. And also there's one small issue that what happens if the Hessian matrix is not immutable, then you cannot apply this method. But there are some ways to go around this. This is not actually a big issue, but the other two, the other one is the issue that it converts to certain points is the biggest issue for this method, because then it means that you cannot apply this to find local to find minima. And then in deep learning or applied to deep neural networks, many popular algorithms, maybe the one you heard a lot is ADA. They are gradient gradation. They are first order methods. And why they prefer? So one thing is because first order method, you need to compute gradient, and gradient you only need the complexity is just the same as the dimension of your problem. First of all, you have deep neural network with like 10 billion parameters, so the dimension is 10 billion. And then you compute the gradient at one point, it will cost you about 10 billion. But now if you want to do like second order method, you need to compute the Hessian. And so it will be n squared. You need to compute matrix. So matrix will have dimension n squared. And it will be 10 billion times 10 billion calculation you need to do. It's a lot more than first order method. And then the second thing is that people found that for problems that they work in deep learning, then first order method already gives you a good result. And maybe it may have something with the data set, we don't know, and also maybe with the structure of the deep neural network, probably. And so for second order methods, because the complexity is too big, so usually you cannot even use it. Not mentioned in that they don't give you good result. And the one that you might hope to use in such big dimension currently is the BFGS. So it's maybe the less complexity among all the second order methods, but the result for this one is not good for deep learning. Of course, this not, but in smaller dimensions than second order methods, maybe competitive compared to first order method, because as we mentioned, second order method, they have the tendency to be quick, they converge quickly, while the first order method may converge very slow. So in small dimension and in higher dimension, you may need to do more research in order to be able to use the second order method. So maybe in the future. Now we have now let's say we have a method, theoretical method, and it's not good. It doesn't have convergence. So how can we boost convergence? So one way is you first Okay, so you already use direction Wn to move. So what I mean by this direction Wn, so let's come back to first of all gradient descent. Gradient descent, so the Wn is the gradient of x at xn. And for the Newton method, the Wn is this Hessian matrix inverse times the gradient. So that's what I call the Wn. And then so we know that we should move to that Wn, but then we don't know how much we should move. So for that we put in something called alpha n for the learning rate. And the thing is that we need to choose a good learning rate in order to have convergence. So how could we find a good learning rate? So one good method is, so several methods. So one is also you could use the exact line search because you want to find minima. So maybe a good way is to find the alpha n to be so that this alpha n will be minimum for this function in one variable alpha f xn minus alpha wn. So it's called exact license. But even though it is for each step it gives you minimum, but in globally it the sequence n that you get might not converge any. So even though it seems good, but you cannot prove that it's convergence in general. And another method with the more general than this, they call the just region. So you what you do is that you have this yeah, okay, maybe I have something maybe I should so you have Wn and then you put a bound on this alpha n. So how much you want to go? So for example, you say alpha n should be less than absolutely should be less than equal 1, and then it means that you do all the alpha n all the w inside this so that it's minima this function fw like this. So it's called just so you look around your xn and you move only a little bit outside inside a ball, and you find a minimum for this. And again, it might look good because you can find at this point you find minimum. But again, if you look globally, you look at the sequence that you construct by this way, you don't know if you can prove it convergence or not. And also, what is not good about these two methods is that implementation might be a problem because for the first one, you need to find a minimum, which means that you are working on a small on a sub problem, which also requires you to find minimum. And the second one, it has several problems. First, you need to choose what is the radius of the ball that you want to work with, which is Rn, and how can you find Rn? And secondly, you need to find minimum on this ball, which is also no trivial problem for this. Now there's another method called the Amister connection, which is very simple. If you know that Wn time gradient of f at the point xn is strictly positive, then by calculus, so you just use Taylor expression. You can find some alpha 0 so that if for all alpha n less than equal alpha 0 and because that goes 0, then you have this fxn minus alpha wn minus fxn plus this alpha times wn has gradient fxn over 3 less than equal 0. And that is the value, consider the value at the new point, that is xn minus alpha wn is less than the value of the function at the fxn. That's the point xn, which is good because you want to find minimum, right? So maybe if the next point, the value of the next point is smaller, then maybe it's good. And not just that, but here you have the depression is might be kind of optimal because this is by Taylor expansion. The order of this alpha WN inner product with graded. It might be the best you can do. If you don't care about the division by 3, so it's the best you can do. And this is actually you can implement it in practice, and it's very easy. So how you can do it? You can use a simple sorter. You could start from alpha equal 1, and you check this condition. You check if it's satisfied or not. If not satisfied, then you divide alpha by 1, by 2, so it's become 1/2, and you put in and you check this condition again, whether it's satisfied or not. If it's satisfied, then you choose that to be your learning rate alpha n. If it's not, then you divide by 2 again, so now it becomes 1/4, and you check again, and you do again. And after finite number, these checks you will this condition will be satisfied, because what we just said that if alpha small enough, then this condition is satisfied. So then this is a way for you to implement, and it's called backtracking. Why? Because we start from 1 and we check if it's satisfied, then you choose it. If not, we go back. We go to 1/2, and so this if it's, and if you check again, if it's not satisfied, you go back by 1/4, and so on. So this is why it's called backtracking. And backtracking is in general is a general strategy in searching in computer science. If you agree. Yeah.
Có một số nhỏ chia cái ba nó có ý nghĩa gì?
Division by 3 doesn't matter. You can divide by any number provided it's bigger than 1. Yeah. It doesn't matter. It's and then there's one condition that we call warfare condition, which people so usually use. This condition, warfare condition, it includes this little condition plus one other condition which we call curvature condition. And to satisfy this, then usually the learn rate you find from warfare condition will be smaller than the learn rate you find from ambiguous condition, because warfare condition you need more, you need to check more. So this means you might convert slower than if you use ambiguous condition. And secondly, for warfare condition, usually you don't get better convergence result. So in practice, ambiguous condition is one of the best ways you can use to push your convergence of your method. And for example, if you apply this to gradient descent, so for gradient descent, you can apply this because in gradient descent, then Wn is exactly gradient of f, and you know that if gradient f is non-zero, then the inner product of gradient of f and itself will be positive, strictly positive, so you can use this. For Newton method, you cannot apply this because you don't know if the Hessian inverse times gradient and inner product with gradient is strictly positive or not. It depends on the eigenvalues of the Hessian, and also eigenvector. So if your function f is strongly convex or maybe convex, then the Hessian will be positive definite, and in that case, then this inner product will be strictly positive. Then you can use this ambiguous condition. But if your function is not strictly convex, which is the case you usually see, then you cannot apply this ambiguous condition. And then there is another way also another way to push your method, but it's different from the way we described before. And this is used in statistics, for example, one for the gradient boosted tree. So if you remember, you have the tree decision tree. and now you apply this gradient boosting trick, you will have maybe a better model. Or you can also apply this to a forest, random forest. And so what's the difference here is that yeah, I mentioned this because maybe if you will work with machine learning, you apply it in the role, maybe you will see this so-called gradient boosting something, and I explain what it is, so maybe you understand. So in this case, the difference from the ways we described before, what we do is what we have xn, and we put alpha n inside in front of wn. So what we do is that we change the point xn plus 1. It depends on alpha n. But in this kind of for the gradient boosting, you don't change the point xn, but you change the model 0. You change your function. Yeah. So how we do it? So what does it mean? So first of all, you construct a deep neural network, but then it might be not good enough, and then you modify it. So this is the way how you can modify. One way to modify is that so this is so let's come back to the setting of our deep neural network setting, deep learning setting. So we have a data set that goes x1 to xn, and at xi, let yi is the value, correct value for it. And then you have your model, g0 or g. And then you look at this, the ft is the sum of time I, d, yi, gxi. And maybe you want to find t so that it will minimum this distance among all possible models in your space. So then, what you can think that actually you don't need to know the whole model. What you need to know is just because you have finite set of data. So what your model do is it just depends on how it applies to this x1 to xn. So actually, you only need to know what happens to di which you define to be g z xi. So then you have this function which depend on z1 to zm with the values of your model as xi. So now you thinking about like, okay, this is just a user function in z1 to zm. Your variables now are z1 to zm. And then you can apply any method you want to this function. And the difference, you can apply any optimization to this function as z1 to zm. The difference to before that before you could start from any initial point, but now you want to start from g0x1 to g0xn because you want to modify this g0. You don't just want to go from any random point, but you want to go specifically from this point, and you want to get better point. Also, when you apply yeah, so maybe I give you example for this, so it's easier to understand. So let's say you use your matrix yi, half way like yi minus yi to the 4. And then you have a model possible a different network. And then your so before your different network will depend on x and some parameter beta. But now you just write like cx, and you think about it's key to also encode with beta inside. And then you look at your function. maybe I should use the deep neural network, so like E, and then the opposite end. Before, when we start say beta, so if we get beta, it is and say your data is just 2 point, yes, just for the purpose of illustration. So then you will have like E x1 beta minus y1 half square dx that minus y2 half square. And this beta could be 10 billion, like if this is last language model, soon language model could be even 10,000 billion. But now I recognize like depends on beta, I think like okay. So actually this only depends on two numbers. So for this step one, step two. So if you know okay beta maybe in R to like n to the n, that's very big. But now I optimize like with the function from 10 to 10, I just think about like from n, then one set to just two variables. So this is a different viewpoint. Let's just set one, I want to find one square. Set two, find one square. This. So now you have a function of only two variables. If you go at the beginning, you have a function in beta, which is maybe in 10 to the 10 variables. And what is good about this is that now it's very easy to work with it with two variables. And that's the only constraint that I need to start from. So I have my my model that I constructed with. Like for this one is z10, and then it's and now I want to find the values for z1, z2, starting from z10 to z20. So I can apply, for example, if I apply gradient descent from this, so I just apply from this point, and I apply gradient descent to this point, and I go again. So I have sequence, and then maybe I can get the result. So this is for the gradient boosting. But you can also use the Newton method for this, and you can call it Newton boosting or something. Yeah. It's you can apply any optimizing method to this. And yeah, so like I said, this point view is help you to modify your model. You have model that you want to modify it to get a better one. Yeah. So yeah. But anyway, it still it relies to your optimization. Yeah. So I already explained about this. Now we talk to this stochastic optimization, which is an important issue when you work with mini parts in different networks. And so here is an abstract statement of this, and then I will explain about how it works. So in this case, your first function is depends on one extra variable c, which is random, fxc. So if you think about this, like in the setting of the different networks, so one c will be mini parts, and because you choose it randomly, so it depends on the on the distribution of your data set I. Yeah. You can think about C like mini parts, and then in this the thing is it has two variables. One, the main variable x, and then the other variable c, which is random. And then you can apply, you can compute the expectation of this with respect to C, and you get a function called Tx. And this Tx is actually what you want to minimize. But the thing is, in practice, you don't know about this Tx, because you don't know about the distribution C. Maybe you want to find out about C. Possible you have this data set and you don't know about the distribution of how many you have the whole data set of pictures in the world, and you don't know how many pictures will have a cat, how many pictures will have a dog, how many pictures will have a mouse. So you don't know. So this, but you try to find the average. So this is some kind of average of these. And then assume that you have the iterative method IM like before, and it depends on two things. It depends on a function f and it depends on a point x. And if you have that data, you can get the new next point. Now, when you apply this for this kind of stochastic thing, then your function f at the point at the step n, what happens is you will generate a new point Cn depending on the distribution. You see the same as when you run this, when you train a different network. So at this point, you pick out a mini box, you put in your first function. So that is your new first function. That's the same here. So you think about Cn like a mini box that you generate at that point. And then you apply this f to your method to this function f. But now C is Cn and the point xn here, and then you internet like before. And then you want xn to converge to minimum of 3x. So this is maybe what you want. But there is some issue about maybe because this is stochastic, so discussing about converters is not it's quite delicate. We will say later. So here I give you an example so you can understand this. So assume that you have like xt is c plus 1, x squared minus 2x, and c is the normal distribution. So if normal distribution, you know that if the expectation of c is 0. So then if you apply, if you compute this expectation of this at when c is with normal distribution, then you think about x like a constant here. So if you compute e of c plus 1 x squared, it will become x squared because e of c is 0. And then e of minus 2x is just minus 2x. So your function 3x, your average function is x squared minus 2x. And then you apply, you want to apply, possibly you use gradient descent. So you want to compute the gradient with the variable x. But now, yeah, so I'm sorry here, in this formula, xn plus 1 equal xn minus 2, c plus 1 xn minus 2, you should put c to be cn because at this time you will do cn. And now I will give you an illustration for how this gradient descent will do with this example, and we have also other example we do later. And now I will delete this. Okay. So this is the app that I am developing with some people. They also was student here. And the thing is, this one is now it's just for laptop and it's not for mobile. And to use maybe if you want to use it, maybe it's better to look at this user guide first, so you know what happens. And I give you this thing. There's only it is the more you can copy it, and you can check it. So what happens is that for this free version, because we put it on AWS, so it costs resources. So we can only offer some limited application, like the number of variables will be 1, 3, and number. This just means that if you want to solve, because this one it could run optimization, or it could find roots of some system equation. So you can so if you want to use optimization, you put this number of 50 function to be 1. If you want to find roots of the system equation, so this number of 50 function will be the number of equations you have. And it will be also because this we have limited resource, so it has some limited number of time you can run this every day. So we have some limit, and if it is not limit, then you cannot do it. You need to maybe wait till next day, or we also we will put kind of like it actually an executable file here, and you could download it, and you can work on your computer, and it will be basically the same like this on the web here. And if you want more, you can contact us if you want to book more. So now let's do the stochastic minimization, and we do gradient. So we have several methods. So some methods are classical, like gradient descent and the backtracking gradient descent that I just introduced you, and there's so-called regular size Newton. And this relax Newton, if you put this learning rate in one, this relax Newton is this Newton method. And then we have some, so these are classical method, and then we have some better method. And a rule is that if you go down this, then the last one will be usually the best one, but then it would be to take you more time. So you need to do a trade-off. You need to think about like how much time you want to run this, or how good result you want to get. Yeah. So if you want a very good result, you choose the last one. If you want it to run very fast, maybe you do the first one. So let me do with gradient descent, because the most maybe the one that you see maybe most, and then maybe put also work with constraint, but now okay, we don't do any constraint, and we could like possible do 2000 star step to be the limit we put here, because like I said, we have some because this cost it costs to run this on the internet, and you could put 0 here for the initial guess, and you don't need to put this because you don't have constraint. And then now next thing is you put you click in generate, and you put in your function. So now let's see what function you want to go. So for this function, c plus 1 x squared minus 2x. So when you want to do this on this, so the c you will write like y. And for this version, we only assume that the random variable is one dimension. But if you contact us, we could do higher dimension for you. And then for the x, you have only one variable x. So x squared. Okay. So then you put here x, but then you need to put x0 like this. So you see, yeah. And then plus that 2, which means x0 squared, and then minus 2 plus x0. And then you just put click and minimize, and then this let's see why what happened. Oh, okay. Let's see. Like do this one. I don't know what happened. Oh, okay. So let me just maybe this there's some problem with backend front end, but let me just do it on my computer. See the same. Okay. What happened?
Giới thiệu cái tool để thử nốt gì đó, not optimization.
So just wait a little bit. I don't know, maybe people, because yesterday I checked it was okay with the website, but maybe people I just checked it. People
Không share được cái màn hình
they were not in the
chạy trên web nó đang bị
web.
Em mà chị mình có nhắn vô đó mình thầy ơi cho mình xin cái rate của thầy được không? Vậy là biết sao ta?
Okay. So one way you can think basically like new, and then you write in a fancy way. But actually, okay, I explain to you later. Yes. Okay. Yes. So now I can
record.
So maybe you do you see it now? Yes. So now I have this my terminal, and now I run this. So this is wrote in this is written in Python. Yeah. So I have the same like before on the website, but now I run it on my computer, and I use stochastic optimization. I use gradient descent. And then I use number variable 1, 23,001, and I run like 2,000 steps. And initial guess 0, and then raise 1. And then I also have this okay. So I have this one. Yeah, and I can put in this my function. So y plus 1 star x 0 star 0. Yeah. Okay. I'm sorry. I should it should be stochastic. Yes. Then I use normal distribution for y for t. And then minus 2 x 0. And then I have this minimize. I put in, and let's see. So maybe I need to choose again. To what? Yes. Normal distribution. 1, 1. 0 here. Yeah, okay, so now it works. I can show you how can I go down. Yeah, you can see here we didn't bring out the C because if we bring it down it's also too much. But what happens now in this iteration, you have one new value of c. And you can see how the gradient descent goes. So first of all, 0.2, first one, and then you go. Sometimes you could go big, sometimes you could go small because it depends on the speed you get. So here you don't have the same function f. So even though we write fx here, but it depends on speed. But at the end, okay, let's see. Yeah. So yeah, I think it should also have maybe because I do the zoom maybe a little bit. So usually it should also give you the average of each point. Yeah. So now we can check with the backtracking gradient descent. Yes, and you can run again. You use the same function. You can run again. And you see it's like this. So what happens is that okay, we have this function is if you compute the expectation, it will be x squared minus 2x. So you know that the minimum will be after x equals 1, and the value is minus 1. And you see for this one, it's many values are close to 1. Yeah. For the backtracking, so actually backtracking is but in this case, backtracking and this one they work almost the same, and it's not considered because people actually they have some results on this. They prove that if you have a function with the gradient if this is continuous, your function is time convex, and if you apply gradient descent and learning rate is smaller enough compared to the Lipschitz constant, actually 1 over L, then you have the higher convergence in average. But what happens if we put bigger numbers here? Now, if I instead of this function, so I still use 1 as the learning rate for the gradient descent, but now I put 10 times here. So if you put 10 times here, then what happens is that your function now if you compute the expectation, it will become 10x squared minus 2x, and it means that your minimum point now 1 over 10. X equals 1 over 10. And then we check now, let's check with the gradient descent. Okay, what happens to gradient descent for this? And I do the minimize, and now okay, it's run. And you can see for gradient descent, you could go to like 2 and so on, way far away from 0.1. A lot of them go far away from 0.1, which is what you want to get. You want to get 0.1, which is your minimum point, where it go like 1, 2, and so on. And in this case, the condition that people need to prove the result that I just mentioned for gradient descent is not satisfied because now your learning rate 1, and your the Lipschitz constant for your function is like 20. So you want like learning rate less than 1 over 20, but here you don't have. That's why it could be very far away from 0.1. We'll see what you want. Now, what happens if you you see most of them are very far away from 0.1. So what happens if now you use backtracking gradient descent? Okay. Now I run again. Yes. Then I run. And now you can see many times it's less than 1. So it's closer to 0.1. Yeah. So even sometimes it's like 0.5 and so on. So it's closer to 0.1, which is the one you want. So in this case, backtracking gradient descent is better than gradient descent. So you don't see a lot which is 1. In coordination, if you remember, you have many terms where x is 2 and so on. But in this Batakin, most of them are less than 1. You can see. So it's better because your point, the minimum point should be 0.1. And now what happens if, so you can see. So you can see that Batakin is better in stochastic gradient descent, in stochastic optimization. At least for this function. And now if I use the method, we see actually the best one here. This is the last one here. So let's see what happens. And I use the same thing here, and I do minimize. Okay, it runs. Yeah, so now you see, 0.9 is 0.1, so it's also less than 1. Actually, I don't know why, because it should also bring out these average of this point, and why not here? But you can see, it's also less than. Actually, I think in this case, this method and the Batakin is type might be similar. Yeah. And now we can come back to another example. Now, what happens if you do this? X squared plus 2 times 1 plus cx. So now the main point x squared, so they still be they are not changed, but the x this is changed. So let's see what happens to this change. So I come back to gradient descent and I change the function. So it will be x0 squared and minus 2 times 1 plus 6. I don't know. Probably people do something. Minus 2 times 1 plus 1 and then x0. So now if you compare the expectation for this, it is still x squared minus 2x because again expectation of y is 0. So I am here give the sum. So after this example, we can take a rest. Let's see. Okay, if we run it, what happens for gradient descent? Yes. So what we should have that the minimum point to be 1. So we want the point to be close to 1. So let's see. This case, so it's good. It's good because again, in this case, x squared, the elliptic constant is 2 for this function, and you choose the direct one. That's extremely good. Yes, so it's not too far away. Yeah, around it, and I think if you take average of this, it will be around close to 1. Now, if we do like Batakin, it, maybe I don't think I need to do it. Yeah, so this one has been Batakin, and then it is similar like before because in this case, your learning rate is close to 1 over the elliptic constant. So they are the same. But now what happens if I multiply by 100? Maybe every time I should do it. Oh no. Minus 2 10 1 plus y 0. Okay. And then I have gradient descent. I have gradient center. Let's say 100.
Dạ.
And then
Không, tại con làm biếng, con thấy quải quá, con về nhà ăn con online luôn.
Vậy đó hả? Nhưng em từ đó mấy hạn chế.
Dạ thôi, vô chính nhất hả?
So you can see that so you want in this case the expectation function is x squared minus 20. So you want the minimum to be about I think 10, x equals 10. But you see that gradient descent, so most of the cases they are 10.
Tôi là ví dụ
They call
đưa
they,
em
they,
cái mô độ nào rồi mình đưa cái function của mình ít như thế nào đó bấm mình muốn chạy bao nhiêu lần thì nó optimize nó chạy vì cho mình biết mỗi lần chạy
so let's see bucket
số ABC
use bucket.
Nói chung là người ta đã rinh vào cái trang đó.
Okay, just see the name bucket. Yeah, so for bucket also, yeah. Yes. So anyway, so this just illustrates that if you run with stochastic optimization, so you should be aware that every time you run, you might get a different result, because every time you run, you generate different value for t. And so you get a different one. And then the second thing to remember is that if your function is not good, or maybe if your learning rate is too big compared to the existing function, then the gradient descent might not go well. Yeah. So that's why, for example, people want to modify the learning rate when they train deep neural networks. So they want to do it. And the last, we will discuss more on this later, but one thing is you hope that even though each time you run stochastic optimization, you get a different result, but you hope that they should be highly distributed equally in respect to this distribution of C. So somehow you should see some similarities if you run many times. Yeah. Okay, so maybe it's good to take a rest to satisfied.
Tức là cái gì ấy còn đang trên cái thực nghiệm cái làm cái gì này thì cái data nó trên cái làm đúng cái gì, tức là gì cái này là cái như là một cái data vô nó sẽ từ một đó là cái